All right, so we're moving then into a continuation of our subject the other day, Wednesday, where we were looking at the qualitative aspects of Raoult's law, in particular, the qualitative aspects of what happens to a solvent when it goes from being a pure substance to a solution. And we talked about that difference in terms of their intermolecular forces. The solvent particles on their own have weaker intermolecular forces than the solvent-solute intermolecular forces that make up that solution. That's why the solution formed in the first place. From a quantitative standpoint, we bring in something here known as Raoult's law. Raoult's law tells us that the vapor pressure of the solution is directly proportional to two things. The vapor pressure of the pure solvent, so that is the solvent with nothing in it, and its concentration. Now, the concentration in this case is the mole fraction of the solvent. So the more concentrated the solution is, that is, the more solute is present, the more of an impact it's going to have on the vapor pressure itself. But what's really important here, this relationship is completely independent of what the solute is. If it dissolves in the solvent, it's going to have an impact. The impact is going to be based on how it affects the concentration, not based on what intermolecular forces exist between the solute and the solvent. So that's Raoult's law if we are dealing with non-volatile solutes. That is, whatever it is that we are dissolving in the liquid is not volatile itself, does not evaporate. So these would be things like salt in water, sugar in water. If the solute itself is also volatile, then what happens is basically we run Raoult's law on each individual component in the solution, and we add together all of the individual vapor pressures. So what this essentially amounts to is a weighted average. Dress this up a little bit different, and this would look exactly like the average mass calculation that we used to do in chapter 2 for the periodic table. In that case, it was proportion times mass, proportion times mass, proportion times mass, added up all together. Here, it's proportion times pure pressure, proportion times pressure, proportion times pressure, added all together. So individually, each one of these would represent an application of Raoult's law for each of the components. So the total vapor pressure is going to be lowered, but it's going to be lowered in the sense of it's going to be an average of all of the components. So it's going to fit in somewhere between the highest vapor pressure and the lowest vapor pressure. It's going to be somewhere in the middle. Where depends upon the calculation, the proportion of one component to the other. All right, so let's take a look at an example here. We've got a solution that contains 100 grams of water and 25 grams of ethanol. We need to know what are the mole fractions of water and ethanol, and what is the vapor pressure of the solution at 25 degrees Celsius. We are told that the vapor pressure of water is 23.8 torr, and that the vapor pressure of ethanol is 58.7 torr. Since we are given two vapor pressures, this would fall into the category of the second type. I've got two volatile substances. So my equation is going to be that the total pressure is equal to the mole fraction of water times the vapor pressure of water plus the mole fraction of ethanol times the vapor pressure of ethanol. So I've got some calculating to do. I've got to find the mole fractions for each, which means first I got to figure out how many moles of each thing I have. So 100.0 grams of water, 18.02 grams in every mole. 100 divided by 18.02 is 5.549 moles of water For the ethanol, I have 25.00 grams of ethanol and 46.08 grams of ethanol in 1 mole. 25 divided by 46.08, 0.5425 moles of ethanol. To find the mole fraction of water, I need the moles of water, 5.549. Divide by the total number, 5.549 plus 0.5425 would be 6.092. Which would be 0.9109 as the mole fraction of water. The mole fraction of ethanol would be 1 minus 0.9109, which would be 0.0891. I could have found the mole fraction of ethanol by taking that 0.5425, dividing it by 6.092. However, since there are only two components in that solution, if one of the components makes up 91.09%, the other one would make up the remainder, the 8.91%. So logically speaking, I could do subtraction, which is a lot faster than the division. So now I got to put all this together. My total pressure is equal to the mole fraction of water, 0.9109, times its vapor pressure, 23.8 torr, plus 0.0891, the mole fraction of ethanol, times its vapor pressure, 58.7. When you're doing this calculation, sig figs become vitally important because you are going to do a multiplication, which is going to require a round. And then you're doing an addition, which is going to require an additional round. Remember, anytime you switch between multiplying and dividing and adding and subtracting, you have to make your adjustments in between. You can't just carry out all the decimal places because that's actually overestimation. So 0.9109 times 23.8 to three significant figures is 21.7 torr. 0.0891 times 58.7 is 5.23 torr. Put those together, rounding to one decimal place because that is all that is possible out of the first. We get 26.9 torr. So, as I mentioned before, the value that we get squeezes in between the two vapor pressures of the two components. Since water made up the majority of the solution by quite a significant portion, we can see that it is definitely shaded toward the water as opposed to toward the ethanol. So the vapor pressure of ethanol gets dropped considerably because of the increase of attraction to the water molecules. And the vapor pressure of the water really doesn't change that significantly. Now for Raoult's law kinds of problems, these are about as complicated as they get when you have multiple volatile solutes. Any questions about this one? If you can do this one, you can pretty much do any Raoult's law problem. Like I said, this is about as complicated as they get. All right, let's look at another one. I'll let you try this one for yourselves. We've got a solution with 100 grams of water and 25 grams of sodium chloride. What is the vapor pressure of the sodium chloride solution? From the previous slide, we know that the vapor pressure of water is 23.8 torr. Now, before you get too deep into this, what is the vapor pressure of sodium chloride? Don't Google it. You should know the answer already. Does sodium chloride evaporate? No. So its vapor pressure is 0. It's not volatile. So this is the first type of reaction. If you're not given a vapor pressure for the component, we can assume it's non-volatile. So in this case, the pressure of the solution would be equal to the mole fraction of the water multiplied by the vapor pressure of the water, the pure water, which would be 23.8 torr. So go ahead, chew on this for a few minutes, and let's see what you come up with. All right, so this is what it should look like for you. Now, most of you were in this stage right around here, where we could see how many moles of everything we had. Some of you got tripped up here trying to find the mole fraction. Remember, you need the moles total in that denominator, not just the moles of sodium chloride, not just the moles of one component. It's the total in the denominator. The other place where we made some mistakes, I saw some of you calculating the mole fractions of sodium chloride. Yes, you can do that. In this case, it's completely useless though. And the reason why is the vapor pressure of sodium chloride is 0. The mole fraction times that vapor pressure would also be 0, which is why we just leave that part off. So, you know, technically speaking, all of your Raoult's law would look like that. P1 times mole fraction 1, P2 times mole fraction 2, plus P3 times mole fraction 3. But for all the ones that are non-volatile, those products are all going to be 0 because the vapor pressures are 0. And so we can just leave them off. And so if we have a solution where the only solute is non-volatile, then all we have to worry about is what happens to the water. In the end, we'll get a solution here, 22.1 torr as its vapor pressure. So the presence of that amount of sodium chloride, which is a lot of sodium chloride in that amount of water, even so, it doesn't have that big of an impact because from a molar standpoint, the majority of the moles in that solution are still water. Right. Any questions with this example? All right, let's talk about it a little bit then. Let's talk about how we can use this. So Raoult's law has a couple of different applications. One of them is something we call fractional distillation. With fractional distillation, what we are using is we're using differentiation of boiling points to help separate components of a solution from each other. Now, where this is most common is in the process to help separate crude oil into the things that make us go. So in particular, what we see in these cases, this is called a fractioning column here. The crude oil comes in at the bottom, and basically this is a heating column. As we go up the column, the temperature actually starts to decrease. So it's really, really hot up down here. And so it pushes all of those things that are volatile up in the column. And then as we go higher in the column, the temperatures start to decrease. And so the things that are heavier, that have larger molecular weights, and require that higher temperature start to kind of fall off, get pushed off to the side. The things that have lower molecular weights and do not require nearly as high of temperatures continue to rise up into the column until they get up to the top here, and then we either separate them into liquefied petroleum gases, or they get fractioned off into things like gasoline and other fuels. And so you can see, as our molecular weights, as our number of carbons increase, they won't travel nearly as far up the column. Now, this can be done on a smaller scale. Those of you that take organic will use this in some form or fashion. This is a fractioning column here. It's usually filled with a series of beads or other kinds of things in the glassware to help to condense and collect material. And eventually what happens is the one that has the lower molecular weight continues to rise up the column and eventually hits the condenser here, starts to fraction off. And the things that are heavier, as the temperature cools, because we're getting further and further away from the heat source, they start to continue to fall back down into the vessel here. Let's look at another impact of Raoult's law. You remember from chapter 6, this idea of phase diagrams. Well, let's look in particular at a phase diagram. So I'm going to outline in black the phase diagram that existed for this substance as a pure substance. And I'll put here in yellow where it is after we've introduced some kind of non-volatile solute. So what we can see here is that there is a gap between the pure solvent and the solution in terms of its boiling point and in terms of its freezing point. Now, a question I have for you is why? Why is this the case? Why do we see lower freezing points and higher boiling points for our solutions relative to our solvents? Jaren? Okay, and that's essentially it. If you remember back to chapter 6, we kind of stated a general axiom with regard to intermolecular forces and the liquid phase. The stronger the intermolecular forces are in a substance, the more likely that substance is to stay a liquid, which means it tends to have lower freezing points, higher melting points, or lower melting points rather, and it tends to also have higher boiling points. Now, we've already kind of rationalized the top end of the spectrum. Vapor pressure lowering means increase in boiling point. But the freezing point dropping is another something that we really haven't considered. We haven't really talked about the phase transition that goes between the liquid phase and the solid phase. Most of our discussion with intermolecular forces focused on the phase change between liquid and gas. Now, based on what we see in this phase diagram, we can see there is definitely a decrease in freezing point. There is definitely an increase in boiling point. We can attribute both of these to increases in intermolecular force. So for boiling point elevation, we already talked about this. The increase in intermolecular forces drops the vapor pressure, which is going to in turn raise the boiling temperature as well. With freezing point, because we've got those stronger intermolecular forces between the solute and the solvent, they are going to stay in the liquid phase longer. Now we call these two phenomenon the boiling point elevation on the boiling side and the freezing point depression on the melting side. Now what's interesting about both of these is that from a standpoint of calculation, they're very similar in how they are calculated. Both of them are dependent solely on two factors. The first of which being a constant, Kb for boiling point elevation. This is a constant related to the identity of the solvent. And Kf for freezing point depression, again, related to the solvent. An other factor is molality. And the molality is just a concentration. Again, we haven't said anything about what the solute is. All we have stated merely is that the concentration has a direct impact on the freezing point or the boiling point change. So this value, delta TB or delta TF, these represent the changes in boiling or freezing point. And that's an important distinction to make because very often it is confused that whatever we get out of this calculation is the boiling point or the freezing point for the substance. And that is not the case. This is just how much it has changed. So in the case of boiling point, if I find out that my boiling point elevation is 3 degrees, that doesn't mean that my water solution now boils at 3 degrees. It now boils 3 degrees higher than it was, which if it boils at 100 would mean that it now boils at 103. In the freezing point depression, again, same thing, does not give us the new freezing point, instead gives us how much the freezing point is depressed, how much lower it is now than it was before. So again, if my freezing point depression is 3 degrees, it doesn't mean that the freezing point's 3 degrees. It means it's 3 degrees below normal. 0 degrees is normal. -3 would be the new freezing point. Here are some common values for the constants. Now, the values of the constants themselves, you can see there is a direct tie to intermolecular forces. Substances that have stronger intermolecular forces do tend to have lower values of Kb and Kf relative to things that are weaker in their intermolecular force. So you take a look at something like carbon tetrachloride. Carbon tetrachloride, I've got a Kb value of 5. Everything else is in and around 3 or lower. I've got a Kf value of 29.8. Everything else is at 5 or lower. Carbon tet is one of two here that is nonpolar, benzene being the other. But benzene with its ring-like structure actually has some pretty good ring-ring stacking that allows it to have some better intermolecular forces than what you would expect because of that ring planar structure. Let's do an example here. Cinnamon. owes its flavor and odor to a compound known as cinnamaldehyde. Formula for cinnamaldehyde is C9H8O. What is the boiling point elevation for a solution of 100 milligrams of cinnamaldehyde dissolved in 1 gram of carbon tetrachloride? So here, delta TB is equal to KB times molality. I've already got the KB value. I need to figure out the molality. 100 milligrams is 0.100 grams. Cinnamaldehyde, got to figure out its molar mass. Carbon is 12.01 times 9. Hydrogen is 1.01 times 8. And oxygen is 16. 132.17 grams in 1 mole. Would be 7.57 times 10 to the negative 4th moles. My molality would be 7.57 times 10 to the negative 4th moles of cinnamaldehyde divided by kilograms of carbon tetrachloride, which would be 0.00100 kilograms. My molality here, 0.757 molal cinnamaldehyde. My boiling point elevation then, delta TB is equal to KB, 2.34 degrees Celsius per molal, times 0.757 molal. My molality cancels. I'm left with just degrees Celsius. 2.34 times 0.757 would be 1.77 degrees Celsius. So that's how much my boiling point would increase, 1.77 degrees. If I circle back one slide, I'll find that for carbon tetrachloride, its normal boiling point is 76.8 degrees. Which means that for this solution, it would be 76.8 plus an additional 1.77, which would give us 78.6 degrees Celsius for the solution. That wasn't technically asked for in this particular problem, but it's not an uncommon It's not an uncommon question to be asked. Feel like I need to do a vaudeville act up here sometimes to keep the lights on. All right, any questions with this? All right, before we go on to example 6, we'll actually do example 6 on Monday. I want to integrate one other concept. And for that concept, I'm going to need to go to the whiteboard because we're really not ready for anything else. It's something called the Van't Hoff factor. The Van't Hoff factor comes into play when we start to look at total concentration. In particular, ionic compounds. Ionic compounds, because they split into ions, are going to have different levels of total concentration than other kinds of materials. So if I take sugar, for example, I will get one molecule dissolved for every one molecule that's present. Because when a sugar molecule dissolves, it just goes into solution. It doesn't break apart along the way. But when I look at something like sodium chloride, every molecule of sodium chloride that dissolves gives me 2 moles, or rather 2 ions present in solution. Now you'll see this referred to often as total ionic concentration, total ionic charge. Basically, total ionic concentration is the molarity of a solution multiplied by the number of ions per molecule. And the Van 't Hoff factor is estimated by the number of ions per molecule that we get. And I'll say it more broadly, number of particles. So what this means for covalent compounds, my Van 't Hoff factor is equal to 1. For ionic compounds, my Van 't Hoff factor is approximately the number of ions per molecule. This factor is going to come into play when we start looking at freezing point, boiling point, osmotic pressure for these kinds of ionic compounds. We'll talk more about it on Monday in our wrap up. But I wanted to kind of leave that in there because we really can't do the next couple of example problems until we have a handle on that concept overall. Have a good weekend.